morning again. This is Dr. Jingbo Louise Liu from Texas A&M University, Kingsville. We are going to continue to discuss Chapter 7 about chiral molecules. Last class, we essentially showed you how to determine R and O S configurations based on Kahn in gold Prelog's rule. Generally speaking, in order to determine the RS notational system, we need three major steps. The first step is you are going to rank the substituents at the chiral carbon center. The step 2, you are going to rearrange. You are going to orient the molecule so that the lowest ranked substituents, such as your hydrogen, pointed away from you. The last point is you are going to count the different substituents from highest priority to the lowest priority. Clockwise path yields the absolute configuration, which is R. Otherwise, counterclock path is going to produce a S configuration. We have this molecule related to a cyclohexene. So you have 4-methyl cyclohexene. How do you determine RS configuration? First of all, you are going to determine which carbon is a chiral carbon. Let's see, double bonded carbon is considered as a carbon bonded to other 2 carbons. So this, imagine this is my carbon 1. Carbon 1, 2, 3, 4. My carbon 1 is bonded to other 2 carbons, meaning this carbon 1, carbon 2, they are not chiral. Carbon 3, you have 2 hydrogens, not chiral. Carbon 4, from my reading, seems to be a chiral carbon. And then carbon 5, 6, they are not chiral. How do you determine the priorities about this hydrogen, methyl, and this side of a group and the other side? So we are going to use the Kahn in gold Prelog rule. From the right hand side, so you have this carbon number 4 connected to CH2CH and a double bond. Double bond meaning 2 carbons. On the right hand side, I labeled it in pink color, so you have your carbon 4 chiral carbon, possibly chiral carbon. We are going to determine it. And then connected to carbon CH2, both first connection is the same. And then you are going to figure out the first point of difference. So you have a carbon CH2, the other one is CH and the carbon. And then you have CH2 connect to carbon, meaning this group you have higher priority. And then this second one, the second priority, your methyl is the smallest one. So you are going to rank the substituents at this carbon chiral center. And then you are going to reorient it. So you orient your molecule. So therefore, the hydrogen, the smallest substituents pointed away from you. And you ignore this hydrogen. And you are going to count your different substituents in a direction which is in decreasing in priority. So highest one counted to the lower one and the lowest one. So this path is a clockwise path. Clockwise path yield an R configuration. If you have a larger molecule, have lots of carbons, lots of time this absolute configuration is not easy for you to denote it. So if you have smaller molecules, such as you only have 1 carbon connected to 4 other different substituents, so you can use the absolute configuration. But if you have larger molecules, possibly Fischer projection is better for you. How do we determine a Fischer projection? So again, let's take a look at this molecule called bromochlorofluoromethane. So this is the absolute configuration of these 2 different types, R and F configurations. And then you are going to convert this configuration into a facial projection. So here is your rule. For a facial projection, molecule is oriented. Therefore, the vertical bond at the chiral center are directed away from you. And the horizontal bonds are pointing towards you. So the chiral center is the center of the cross, which you are not going to specify it. So this is your carbon. This cross is your carbon chiral center. You don't have to specify it. So my R configuration. So for this R configuration, you have a chlorobromo. This chlorobromo pointing towards you, from you to the blackboard. And the fluoro and hydrogen, they are away from you. In that case, you put hydrogen and fluoro on the vertical bond. So Br and Cl, chlorobromo, you put them in the horizontal position. So again, pointing from you, towards you. And the second molecule, the S configuration. So what you are going to do, S configuration, and you simply switch R and the chlorobromo position. So your chlorobromo, again, you put them in the horizontal position. On the other hand, the hydrogen and fluoro in your vertical bond. So that's how essentially you are going to determine the facial projection. So these different chiral molecules, particularly the ones with the mirror image, which cannot be superimposable. So in this case, you call them enantiomers. Those enantiomers, they can have different others. They also can have different optical properties. So I showed two commonly used natural products. So they have different configurations. So give you a different smell or possibly different optical properties. So each of the enantiomers will react with the receptors in the nose differently. So the chiral recognition, which is commonly occurring in the nature, so again, has one isomer, one enantiomer, which particularly interact with the receptor in the nose. And there's some drugs or medicines, they also have chiral center. So two examples are ibuprofen and thalidomide. So one of the isomer, such as the S, ibuprofen, which is the painkiller. The other one, R configuration, does not have this effect. And also the second drug, so can be used, especially the R configuration, can be used for the anti-nausea treatment. The S configuration, on the other hand, can result in the birth defects. So you need to know the configurations and the molecular structure and their medical effects. So if you have a further enlarged molecule, such as this biphenyl molecule, 1,1' binethyl, so these different molecules, they can have a chiral axis. Chiral axis refers to an X about which a set of molecule or group is arranged in the way, so you can see the spatial arrangement is not superposable. So on the mirror images, and the substituted compounds so may have a chiral X or chiral axis, and therefore you are going to figure out there are two non-superposable enantiomers. And also you may have some other molecules. If I have this biphenyl types of molecule, so you have no substituents. In this case, this molecule is considered non-polar, but this carbon-carbon single bond can be rotated. So meaning if you have different conformations, those conformations can interchangeable. On the other hand, if you have these substituents, such as your AB, XY, they're no longer the same as your hydrogen, so you have different substituents. different configurations, different conformations cannot be interchangeable, and the configuration is locked. The formula is fixed. So that's, the conformation or the structure is fixed. That's another important point. Followed by, we spend a couple more minutes to discuss about reactions which can create chiral centers. Many of the reactions we have been examined from the previous classes so far often form the chiral centers, such as you have your alkene, which is subject to the oxidation reaction, such as your propene, which is oxidized under this oxidizing agent. You form 1,2-epoxy-propane. The first molecule reactant, your propene, is an achiral molecule. After oxidation or epoxidation reaction, you are going to form a chiral molecule. So again, central carbon of the epoxide is a chiral center. This central carbon is a chiral center because this carbon have connected to 4 different groups. Another reaction, related to another point related to this chiral center creation. So also we already knew the alkene is considered a planar structure. So you have your oxidizing agent such as peroxy acids. These peroxy acids can attack to this carbon double bond from either top or bottom. So therefore you form 2 different configurations. One is R, another one is S configuration. These 2 configurations, they are going to have the same probability. Therefore, your product yield will be 50%. So there are some other examples, such as you have your addition reaction. So to your alkene, you have a 2 either cis or trans 2-butene. You have 2 butene molecules. Can be a cis, can be a trans molecule. You are going to allow the hydrogenation addition to occur. So therefore, you can produce a 2-bromobutene. This 2-bromobutene, this second carbon, is a chiral carbon molecule. You are going to produce a chiral carbon, and also you are going to produce 2 different configurations, R and S. R and S configuration, again, they both have 50%. Therefore, in your product, you are going to produce a mixture. This mixture composed of 50% of R configuration, another 50% of S configuration. You consider the 1-to-1 mixture of 2 enantiomer will be produced. Therefore, the whole system, the whole mixture is a racemic mixture, meaning if you have an optical property, both molecules are going to polarize the lights. The polarization will be cancelled out. Similarly, if you have the chlorine reacted with butane, so butane, so you subject to the substitution reaction. So you produce 2-chlorobutane. Initially, your butane has no chiral molecule, and then after this substitution reaction, you produce 2-chlorobutane. So this 2-chlorobutane also has 2 configurations, R and S, and also is a chiral molecule and produce a racemic isomers. It's a mixture. And then the other reactions also create chiral centers, such as you have this called fumaric acid. You have a double bond carbon. So what happened under the catalyst? So these double bonds reacted with water. You subject to the hydration reaction. So also you are going to form something we call malic acid. So you have a S configuration. You possibly also have R configuration if your catalyst is not selective. So in this case, you use enzyme as your catalyst. You selectively produce S-malic acid. So this is about the reaction which produce the chiral center. if you have larger molecules, you may have more than one chiral center. For example, I have this new molecule, which is named as 2,3-dihydroxybutonic acid. You have your carbon 1, 2, 3, 4. Let's see. Carbon 1, you bonded to you have a carbon double bond, meaning this carbon 1 is not a chiral molecule. Carbon 2, so you bonded to a hydrogen, to OH, to this group, and to another group. Carbon 2, carbon 3, you can see they are chiral molecule. Carbon 4, chiral centers. Carbon 4 is non-chiral center. So what's going to happen? You have 2 chiral centers. So you are going to have more opportunities to form different types of isomers. In this case, 2 chiral centers, so it's going to be related to different RS combinations. Totally, this product has 4 different stereoisomers. You have 2R, 3R, 2S, 3S. These two, they are called enantiomer. You have 2R, 3S and 2S, 3R. These two also called enantiomer. This 2R, 3S, 2R, 3R, 2R, 3S. These two called diastereomer. Your 2S and 3S and 2S, 3R. These two molecules, they also isomer, they also called diastereomer. We have 2 different kind of definitions. So one is called enantiomer, another one called diastereomer. Let me move on to another configuration, so called diastereomer. What you can see, number 2 and number 3. Number 2, number 3 carbon both chiral center. They both are like a 2R, 3R configuration. And then you have another molecule, meaning R3 and the carbon 3, carbon 2, both you rotated by 180 degrees. So you receive the 2 enantiomer. This molecule, this number 1, number 3, these 2 isomer, they're also called stereoisomer. But what you see, pay attention, carbon 2 is still 2R, still R configuration. Carbon 3, one of them is 3R, another one is 3S. In this case, 2 chiral centers, you have only one of them subjected to the rotation, 180 degree rotation, meaning this number 1, number 3, they are not diastereomer. They are not enantiomer, but they are called diastereomer. So you have 2 groups of isomers, particularly these stereoisomers. So let me show you. One group is called enantiomers. Second one called diastereomers. So enantiomers and diastereomers, they both are stereoisomers. They are optical isomers. The first one are the mirror images of each other. With 2 stereo centers in the molecule, the enantiomer has a configuration changed on both carbon chiral center. That carbon chiral centers are the stereo centers. Your enantiomers have the equal but opposite spatial rotation. On the other hand, your diastereomers, they are also stereoisomers, but they are not mirror image. The first ones, the enantiomers, they are mirror images. And with the 2 stereo centers in your molecule, the diastereomer has a configuration changed only for one of the stereo carbon chiral center. Diastereomers have different magnitude, different direction of the specific rotation. So this is the 2 different types of stereoisomer. So if you have more than two or more different chiral centers, if you have larger chiral centers, larger molecule, so facial projection will be more applicable for you to express the absolute structure. How do you draw the facial projection in this case? So here is our rule. You have this 1,2-dihydroxybutonic acid. So what you are going to do, first of all, you find the carbon with the lowest number. So this carbon bonded with this carboxylic group, which is named as number 1, and then number 2, number 3, number 4. You place your structure, therefore the lowest numbered carbon is on the very top. You put your carbon on the very top, either way on the top. And then you are going to arrange your horizontal bonds to be facing towards you. So you arrange your horizontal bonds to be facing towards you. And then the third step, you are going to flatten your molecule and draw it out. So you draw a structure of carbon with the lowest number on the very top, and then draw a line, draw another line, and draw the last carbon, represent 4 different carbons. And in your horizontal bonds, so meaning the bond facing towards you, like a huggy position. So that's how you are going to draw it. The last step, you flatten it out. For different configurations, you can have a different approach to draw the Fischer projections. Within your Fischer projections, we need to note there are 2 different types of isomers. So one type is these 2 like substituents. They are located on the same side. You call those isomers the erythral. Erythral isomers are the isomers with the like substituents on the same side. If you have these two different like substituents, OHs, they are located on the opposite sides. You call those isomers 3 and 4 called threoisomers. These threoisomers have the like substituents which located on the opposite sides of your molecule. And then most of the isomers, they have different physical chemical properties. For your diastereomers, the rotation, or I would say polarization of light, possibly will be different. So other physical properties may be also very different. For example, if you have one of this molecule, this is a 3-amino-2-butanol. This isomer is normally a liquid. The other one, 2R3S, so you have different configurations. This molecule actually is a solid molecule. Physical properties and optical properties, they may be different. And also I have a couple more examples for you. I will leave this 1-bromo-2-chlorocyclopropane. You also have 4 different isomers. So you can compare them to determine the enantiomers, diastereomers. So that's leave it to everybody to study. I have one more question for everyone. May not be one more question, maybe a couple more questions. One more key point for everybody. I have this 2,3-butane-diols. You have diols. This number 2, number 3, both carbons, they are chiral carbon. You have 2 chiral centers. To determine the number of chiral centers, normally you use 2 to the power n. Meaning this molecule theoretically should have 4 different isomers, but in the real world, you only have 3 of them. So you have this 2R3R23 butane-diol. You have 2S, 3S, 2,3-butane-diol. You have 2 of these. They are enantiomers. You have one more isomer called meso 2,3-butane-diol. So why you don't have 2R3S, 2S3R? Why not? So the compound for this C has a plane of symmetry. If you have a plane of symmetry, this molecule will be superposable. Will be superposable on the mirror image. So therefore, this molecule can this molecule, this carbon chiral center, this whole molecule, we consider it achiral. This molecule, you name it as a mesoform. So you name it as a mesoform. Therefore, you have only 3 different isomers for these 2,3-butane-diols. Just again, be cautious whenever you form a plane of symmetry or center of symmetry. You may not have the isomers. They may be the same molecule, or when you change the 180 degree, when you rotate it by 180 degree. And also for these 2,3-butane-diols, you can use a Fischer projection to represent these 3 different structures. So in the last case, the dashed line represents the plane of symmetry. This molecule is again named as meso 2,3-butane-diols. They are diols. And similarly for this molecule, for this 1,2-dibrommocyclopropane, you may also consider whether you are going to have a molecule with a plane of symmetry. So double check, do you have a plane of symmetry? If you do, you lose 1 isomer. So meaning that you rotate it by 180 degrees, that molecule is the same. Particularly this cis-1,2-dibrommocyclopropane, this has no other diastereomers or enantiomers. And then if you have much larger groups, so in this molecule particularly, you have 4 chiral centers, 4 sterol centers. In this case, your isomers will be 2 to the power 4. The maximum isomers for these chiral carbons. So for the molecule with chiral carbons, you may have the isomers to be determined by 2 to the power n. 2 to the power n. If you have 4 different chiral centers, the maximum numbers should be 16 isomers. So you have sterol compounds. You may find multiple sterol centers. In this case, you imagine you have a large quantity of different isomers. For example, one of these is called cholic acid. You have 11 chiral centers. You may go home, double check which ones are the chiral centers. Totally, the isomers will be 2,048 different ones. So this is essentially about the isomers. For your alkene, you may also have some isomers. Alkene, and especially after related to some chemical reactions, you may find the enantiomer and diastereomers between different ones. So we have several different points, such as this butene, either E configuration or J, either cis or trans configuration. You are going to produce you produce a 2,3-dimethylbutane. So in this case, you may find some diastereomer. So you can use this Newman projection to represent your production. So what you can see, so you have 2 different possibilities for you. You can rotate by 180 degrees, so you figure out 2 different types of isomers. Actually, what you figure out, these 2 different types of isomers, from my standard related, they are actually the molecule is a achiral molecule. The product is a chiral molecule, but you do have 2 carbon which are the chiral centers. And then we also have some other special molecules, such as this 2-methylene cyclohexane. So this carbon double bond can be subjected to the hydrogenation reaction and the catalyst. So what you are going to produce, you also resulted in a sterol selective molecules. So one molecule, this exomethyl molecule, actually this is your cis configuration is a higher product yield. So one of the molecule has higher product yield. And also related to the resolutions of enantiomers. So about 1984, there's a very famous scientist, Louis Pasteur. He is the person who carried out the first resolution using this tartaric acid. So using a microscope and a tweezer, figured out the different structure of your 2R, 3R, 2S, 3S, 2R, 3S, 2S, 3R, different mixtures of the isomers. And then you have a little more about the resolution of some isomers. So followed by the couple more slides, I will leave it for everybody for further study. So generally speaking, I will conclude what we are learning for today related to sulfoxide or kinetics of the isomerization or chiral molecule reactions. So it's not required for our class. It's going to be leaving it for you to further study. Also in your isomers, so there are two different configurations, R isomer, S isomer. They may result in the consolidation of the polarization of your light. Therefore, if you have a one-to-one mixture of your enantiomers, those enantiomers are called racemic mixture. Racemic mixture are optically inactive. Each of the isomers, they are optically active. However, these two together in 50-50% for each, so the polarization of your light will be cancelled out. So that's why you are going to see something called racemic mixture. And also about the specific rotation. So is the rotation, you can adjust it by the concentration and the length of your sample cell. How do you determine the specific rotation? So I listed in an equation for you for future study. So again, that's all for today. Thank you so very much. You have a good day. Stay safe and stay healthy.